The research paper introduces an improved physics-informed neural network, I-PINN, that mitigates gradient-related failures by enhancing the uncertainty weighting method from previous work. The proposed IAW-PINN sets an upper bound on adaptive weights, preventing excessive suppression of residual term weights and avoiding ill-conditioned optimization problems. This ensures convergence and adherence to constraints, improving both boundary condition and residual term accuracy. The I-PINN method effectively addresses the issues of substantial fluctuations in solution outcomes observed in IAW-PINN, significantly enhancing robustness across diverse network structures and improving the model's generalization capabilities. The authors demonstrate that I-PINN significantly enhances solution accuracy, achieving improvements of at least an order of magnitude over PINN, IAW-PINN, and IA-PINN. Physics-informed neural networks, PINNs, have revolutionized scientific computing by integrating fundamental physical principles with advanced data-driven techniques. However, PINNs face challenges with stiffness in gradient flow, limiting their predictive capabilities. To address this, an improved PINN, I-PINN, is proposed, combining the strengths of neural networks with an improved architecture and adaptive weights containing upper bounds. I-PINN achieves enhanced accuracy and accelerated convergence without introducing extra computational complexity. The proposed I-PINN combines advancements in PINN frameworks to enhance the optimization process, convergence properties, and representational capacity. Numerical experiments with various benchmarks illustrate the improved accuracy and generalization of I-PINN. The supporting data and code are accessible, enabling broader research engagement. By employing robust optimization algorithms and meticulously tuning their parameters, I-PINN demonstrates the capability to enhance accuracy by at least one order of magnitude and accelerate convergence without introducing extra computational complexity. The physics-informed neural network (PINN) framework has been widely adopted for solving partial differential equations (PDEs), due to its ability to incorporate physical laws into the neural network architecture. However, existing PINN methods often suffer from gradient-related failures, leading to inaccurate predictions. To address this challenge, this paper proposes an improved PINN, I-PINN, that integrates the strengths of two existing methods: the improved architecture for PINN, IA-PINN, and the improved adaptive weighting method for PINN, IAW-PINN. The IAW-PINN method sets an upper bound on adaptive weights, preventing excessive suppression of residual term weights and avoiding ill-conditioned optimization problems. This approach ensures convergence and adherence to constraints, improving both boundary condition and residual term accuracy. The I-PINN framework effectively addresses the issues of substantial fluctuations in solution outcomes observed in IAW-PINN, significantly enhancing robustness across diverse network structures and improving the model's generalization capabilities. The I-PINN method has demonstrated the potential to reduce errors by at least an order of magnitude and improve the convergence rate, all while maintaining computational complexity comparable to the baseline model. The paper's principal contributions include the enhancement of the uncertainty weighting method, the development of IAW-PINN, and the integration of IA-PINN and IAW-PINN to form I-PINN. This paper also discusses the PINN methodology for solving partial differential equations, PDEs, and its recent improvements. A generalized nonlinear PDE is considered, which includes various types of equations such as fluid dynamics, heat conduction, and electromagnetic equations. The loss function in PINN is designed to contain deviations from initial, boundary conditions and the PDE itself, with weighted multipliers used to balance these components. The paper introduces an improved multi-layer perceptron inspired by the attention mechanism in Transformer, addressing the gradient vanishing, explosion problem encountered by the original multi-layer perceptron when dealing with complex problems. Furthermore, it introduces adaptive loss weight functions based on weight upper bounds, designed to dynamically adjust the weights based on the observed upper bounds of the loss terms during training, thereby improving the performance of PINN on complex problems. The authors address the limitation of fixed weighting in physics-informed neural networks, PINNs, by adopting a multitask learning approach that utilizes homoscedastic uncertainty to adaptively weight different loss components. This approach enables balancing the convergence and accuracy of PINNs. The method establishes a Gaussian probabilistic model with output U, defining a Gaussian likelihood with mean given by the PINN's approximation and uncertainty parameter sigma m. The joint probability distribution over all tasks is maximized, and the negative logarithm of the likelihood function is taken to obtain the desired loss function. The resulting loss function consists of two terms: a weighted loss function for each task and a regularization term to penalize tasks with high uncertainty. Minimizing this loss function enables adaptive assignment of weighting coefficients to each portion of the losses, balancing their various components. The uncertainty parameter sigma m represents the uncertainty of each task, with easier tasks assigned higher weights and more uncertain tasks assigned lower weights. However, the authors note that the initial loss function may lead to a scenario where one loss consistently dominates during model training, restraining the growth of weights associated with residual terms and inadequate training of the unsupervised learning component. To address this, they propose an adaptive loss weight function incorporating upper bounds, inspired by previous work. The modified loss function introduces a weight upper bound gamma, preventing the weight term from diminishing to zero. This approach serves two purposes. It prevents the weight term from vanishing and ensures that difficult tasks are not ignored during training. The final loss function consists of three components: the weighted loss terms for each task, the regularization term, and the log likelihood term. This adaptive weighting approach enables PINNs to learn from multiple tasks with varying uncertainties, improving the overall performance and accuracy of the model. The proposed IAW-PINN approach introduces a weight-based upper bound to constrain the magnitude of the weights, preventing any single loss term from dominating the training process. This allows for optimal training of both the initial, boundary loss term and the residual term, enhancing overall model performance. The final loss function is given by equation 18, where sigma represents trainable parameters that can be optimized using gradient-based optimizers such as ATOM or LBFGS. Notably, lambda is defined as 1, sigma caret 2 plus gamma 1, differing from the standard PINNs model. To demonstrate the effectiveness of IAW-PINN, a comparative test is conducted between the AW-PINN method and IAW-PINN using the Helmholtz equation. Figures 13 present the results, showcasing the relative errors in solving U and F using different network structures between the two methods. The IAW-PINN approach with an upper bound gamma equals 10 to the power of 3 outperforms the vanilla adaptive loss weighting method in terms of both the solution U and the residual term F. This is evident in the reduced overall error of the model, allowing it to effectively address both supervised and unsupervised learning aspects. The results indicate that the weight-based upper bound IAW-PINN approach effectively reduces the relative errors in solving U and F, demonstrating superior model-solving performance. The comparison of relative errors in figures 13 highlights the advantages of the IAW-PINN approach over the AW-PINN method. Specifically, the IAW-PINN approach achieves lower relative errors in solving U and F, showcasing its ability to effectively balance the supervised and unsupervised learning aspects. The proposed approach provides a promising solution for addressing the challenges of physics-informed neural networks. The network structure is varied across different configurations, including 3x50, 3x70, 5x50, 5x70, 7x50, and 7x70. The results demonstrate the robustness of the IAW-PINN approach across different network structures, highlighting its potential for applications in physics-informed neural networks. The IAW-PINN method effectively manages the weights of the boundary term and residual term in the loss function, as demonstrated in Figure 5. This is in contrast to the AW-PINN method, which introduces a significant disparity in the magnitudes of these two weights, leading to optimization challenges and potentially impacting the final solution quality. Figure 4. The proposed IAW-PINN mitigates these issues by adaptively adjusting the weights of the loss terms based on their relative importance. A novel framework is proposed by integrating IA-PINN and IAW-PINN, referred to as the Improved Physical Information Neural Network, I-PINN. This integrated approach addresses challenges such as vanishing, exploding gradients during PINN backpropagation in complex problems and mitigates the issue of imbalanced training due to scale differences in multi-objective losses. The I-PINN framework incorporates an improved network structure with adaptive loss weighting methods, as illustrated in Figure 6. The pseudocode for the I-PINN algorithm is provided in Algorithm 1. The algorithm initializes the adaptive weight parameters and learning rate, then iteratively updates the model parameters and adaptive weights using the atom optimizer. Once the model converges or reaches a specified error threshold, the algorithm terminates and returns the optimized model parameters and adaptive weights. The study presents a systematic comparison of physics-informed neural networks, PINNs, and their variants, including improved PINN, I-PINN, improved adaptive weighting PINN, IAW-PINN, and improved adaptive PINN, IAPINN. The Helmholtz equation, a partial differential equation in 2 dimensions, is used as a test case to evaluate the effectiveness of these frameworks. The results show that I-PINN outperforms PINN, IAPINN, and IAW-PINN in terms of relative errors, with values of 2.68 times 10 to the 1, 2.22 times 10 to the 2, 1.21 times 10 to the 2, and 5.26 times 10 to the 3, respectively. Comparative experiments were performed using various network architectures, and the results are presented in Table 1. The table shows that I-PINN exhibits superior performance across different network structures, with its accuracy improving by an order of magnitude compared to IAW-PINN and IAPINN. The figures in Figure 7 demonstrate the performance of 4 different models PINN, IAPINN, IAW-PINN, and I-PINN in solving the Helmholtz equation. I-PINN achieves the lowest relative error, demonstrating its robustness and accuracy. Table 2 presents the relative errors of the 4 models at various k-values after 40,000 optimizations using the atom optimizer, with I-PINN consistently outperforming the other models. Figure 8 compares the relative errors of the 4 models across different network structures, showing I-PINN's robustness to different network structures. The Klein-Gordon equation, a fundamental equation in relativistic quantum mechanics and quantum field theory, is formulated as a nonlinear partial differential equation. The authors employ a network architecture with 7 hidden layers of size 50 and utilize the atom optimizer to train the PINN, IAPINN, IAW-PINN, and I-PINN models over 40,000 iterations. I-PINN demonstrates superior solution accuracy, achieving at least an order of magnitude improvement in relative error compared to the other 3 methods. The authors also investigate the impact of different adaptive weight caps on the performance of I-PINN, showing that as the weight cap increases, the relative error gradually decreases and tends to level off. Figure 9 presents the exact solution, predicted solution, and absolute error heat map for I-PINN, as well as comparisons with PINN, IAPINN, and IAW-PINN, demonstrating the superior performance of I-PINN in solving the Klein-Gordon equation. The results highlight the effectiveness of I-PINN in solving nonlinear partial differential equations, with potential applications in physics and engineering. The paper presents a comparative study on the application of physics-informed neural networks, PINNs, to solve partial differential equations, PDEs, and their variants, focusing on the Klein-Gordon equation and lid-driven cavity flow. The study evaluates the performance of PINN, IAPINN, IAW-PINN, and I-PINN models with different network structures, demonstrating that I-PINN outperforms other models in terms of relative error, especially with a 7 times 50 hidden layer structure and 40,000 iterations of atoms optimizer. Table 3 provides a detailed analysis of the relative error comparison across various network structures and models, showcasing I-PINN's consistent achievement of lower relative errors. The paper then applies the proposed method to the lid-driven cavity flow problem, analyzing the incompressible Navier-Stokes equations to provide insights into fluid motion within the cavity, including velocity and pressure field distributions. The I-PINN model is further evaluated and compared with PINN, IAPINN, and IAWPINN in terms of performance, with Figure 12 illustrating the comparison of loss histories under different adaptive weight upper bounds. The results indicate that I-PINN outperforms other models, achieving a relative error of 5.12 times 10 to the 2. Figure 13 summarizes the experimental results, comparing reference solutions and predicted solutions obtained from different models, with I-PINN demonstrating superior performance in learning velocity components and potential pressure fields. The paper concludes that I-PINN has demonstrated superior performance, exceeding the accuracy of PINN, IAPINN, and IAWPINN by at least an order of magnitude, while maintaining computational efficiency. This novel approach has the potential to revolutionize the field of PDEs by providing more accurate and efficient solutions. I-PINN, a physics-informed neural network framework, exhibits robust performance across various network structures and problem complexities, demonstrating strong generalization capabilities. By integrating an enhanced architecture with improved adaptive weighting, I-PINN achieves stable and convergent optimization for partial differential equations. The framework provides a robust solution strategy for PDEs, but requires further research to explore its potential applications and address open questions, such as the selection of upper bounds for weights. Future work involves examining min-max optimization and improved architectures as alternatives to weight upper bounds in PINNs. Adaptive weighting strategies will also be explored to balance loss components, and the scalability of I-PINN to higher dimensional PDEs and complex physical systems will be investigated. Additionally, I-PINN will be extended to handle multi-scale and multi-physics problems, enhancing its applicability in real-world challenges. Recent advancements in PINNs, including adaptive activation functions, multitask learning, and physics-constrained neural networks, are reviewed. Studies by Jagtap et al., Kendall et al., and Karniadakis et al. Demonstrate the importance of incorporating physical laws into neural networks. Techniques for improving PINN performance, such as self-adaptive PINNs, optimally weighted loss functions, and mitigating gradient flow pathologies, are also discussed. The literature review highlights the growing interest in developing and applying PINNs to various fields. The cited studies demonstrate the need for further research in developing efficient and robust PINN architectures. The references provide visualizations of results, demonstrating the effectiveness of proposed methods in solving various problems. Overall, the literature review provides a comprehensive overview of the current state of research in PINNs, highlighting key challenges and opportunities.